Good evening. Good evening, and welcome to Perimeter Institute here in Waterloo, Ontario, Canada. My name is Kelly Foyle, Educational Outreach Scientist here at Perimeter Institute. It is my sincere pleasure to welcome you to the Mike Lazaridis Theatre of Ideas and Perimeter's public lecture series, both to those of you here in theatre and to our online audience. First, in the spirit of understanding and learning from what has come before, Perimeter respectfully acknowledges that we are located on the traditional territory of the Attawandaron, Anishinaabe, and the Haudenosaunee peoples. Perimeter is situated on the Haldimand Tract, land promised to 6 nations, which includes 6 miles on each side of the Grand River. For those of you watching the lecture online tonight, you can join the conversation on social media. We are at Perimeter, and you can use the hashtag #PILive to chat with Perimeter scientists and to ask questions of tonight's guest speaker. We'll ask questions submitted by our online audience during the Q&A. And now it is my pleasure to introduce tonight's speaker, Dr. Shohini Ghose. Professor Ghose is a leading expert and sought-after speaker in quantum information science, as well as how to make the global science community more vibrant and inclusive. Dr. Ghose is a professor of physics and computer science at Wilfrid Laurier University, the founding director of the Laurier Centre for Women in Science, and president of the Canadian Association of Physicists. She was also Perimeter Institute's first diversity, equity, and inclusion specialist. Among her many honors, Dr. Ghose is a TED Senior Fellow and member of the Royal Society of Canada's College of New Scholars, Artists, and Scientists. In 2019, she was among 25 leading women scientists from around the world featured in a UNESCO exhibit in Paris. Tonight, Dr. Ghose will lead us through the latest advances in quantum world and share her own journey as a quantum scientist. Please join me in welcoming Dr. Shohini Ghose.
Thank you. Thank you. So thank you so much for inviting me here, and thank you for showing up on a cold winter's evening to talk about, light and easy topics like quantum. So I thought, given the topic, we should do a bit of a warm-up. Don't worry, it's not too difficult, but it is a challenge. And today I want to talk about quantum science, but also my own story in this world of quantum physics. So I thought I'd start back in the country that I was born and raised in, which is India, and show you a book from ancient India, written about 2,000 years ago. And here's the challenge. You're not going to recognize the book, although it's actually very famous, because I've encrypted the title by replacing every letter in the title with a different letter. It's an encryption called the substitution cipher. But I've given you some clues, right? This is your challenge. Ancient book from India, very famous. I'm sure you've all heard of it. Any guesses? There's always somebody who gets it. Indeed, it is the Kama Sutra. Well done. So this is, hopefully now you're all warmed up and awake. That's not the only reason I'm bringing this up. Kama Sutra, as you know, is well known as a lifestyle manual. For the younger members in the audience, don't worry about it. It's just ask your parents or your teachers later. They'll tell you all about it. But there's a reason I'm bringing it up. And this is because in this book, there's a chapter which describes how people can secretly communicate with each other using exactly this substitution cipher. And so this is actually one of the oldest known protocols for encryption in history. And that's why the Kama Sutra should be famous, right? Of course. So given this idea of encryption, we've been thinking about this for a very long time. Data is, of course, very important as we know today, but even back then, it was really important to keep data secure. And back then, this kind of a substitution cipher really worked well, because there were no computers. It was really difficult to guess what the substitution protocol is. But eventually, over the years, mathematicians tackled this problem, and Arab mathematicians figured out an algorithm to actually crack this kind of a substitution cipher. And I don't know, perhaps you can guess there's ways to actually cleverly figure out what the substitution protocol is. For example, you can look at the frequency of letters and use that. So I think this is no surprise that eventually this was hacked. So just like encryption is a very old technique, hacking is just as old, right? So this was safe until then. And once this was hacked, then encryptors then decided, OK, we need better protocols. So over the years, what happened is that people started developing more and more difficult, complex encryption protocols. And a lot of them were based on difficult math problems. The idea being, if you can think of a really hard math problem and use that to encode your information, then somebody who wants to hack will have to solve the hard math problem. So this is what was done. And over the years, for example, here's an example of a hard math problem. Does anybody want to try this as your next warm-up? No, please don't. It'll take you a very, very long time. In fact, this takes the world's supercomputers working together many months to actually find the answer to this kind of a factoring problem, where you take some large number and try to figure out what two numbers multiplied together gives you this number. Now, this one was actually eventually solved by supercomputers. Here's the answer if you wanted to know. But this is important because the fact that factoring is a really hard problem is a useful thing for encryption, because this is exactly the kind of problem that's used to encrypt all of your data today. So all of your passwords are safe because in the background, if somebody wants to hack your information, they would have to be able to have the computing power required to solve this kind of a problem, which is all good. But the thing is that computers keep getting more powerful all the time, right? So maybe this is good enough today, but it's not good enough forever. What if there's even more powerful computers built? So it's not, in principle, unhackable. At some point, somebody will build a more powerful computer, and we'll be able to crack this. So that brings up the question, is there a way to build encryption that is, in principle, unhackable, meaning no matter how much computing power you have in the world, you cannot crack that encryption? And the answer is yes, which is why I'm here talking about it, of course. And that answer comes to us from, as you might guess, quantum physics. And the idea here is, let's move away from using math problems to encrypt our data. Because if there's a way to build an algorithm to crack that particular problem, then that's not really going to be unhackable forever. And there's no way to prove that for sure, except for a few problems. It's very hard to prove for sure that an algorithm will not be cracked in the future. But instead, if we look at quantum physics, what if we could use the laws of physics themselves to encrypt data? Then the idea is that if you want to hack that kind of encryption, you would have to break the laws of physics. That's kind of a whole different ballgame, right? So that's sort of what people started thinking about. Now, why would it be possible to do this with quantum physics? Well, quantum theory, as you may have heard, is quite a strange theory, and it's full of rather weird ideas. For example, one of the things that this theory predicts, a fundamental part of the theory, is this thing called the uncertainty principle. And what that says is that you cannot precisely know every single property of a quantum particle, like, let's say, an electron, or a photon, or an atom. And this is not because you cannot measure everything precisely. And somehow, if you have better detectors, you can then know everything precisely. This is part of the theory itself, which means that no matter how good your detectors are, You cannot know everything precisely because it's just not knowable. The universe has this fundamental fuzziness to it. And keep in mind, though, that this is quite a precise statement about uncertainty. Right? There's a mathematical equation. And in fact, the other day I was at a wine store and I found this wine bottle. I should have brought a photo of it. The wine was called Quantum. And the equation was on the bottle. Maybe that's one way to get around uncertainty, right? So the idea is maybe the more you drink, the less you care about uncertainty. Who knows? Kind of like the more you know one thing, the less you know. Anyway, we won't go there. But what this is telling us is something quite fundamental and deep, because this is quite a break from everything that came before in terms of our assumptions about what physics can do. All the physics before this actually was built on this idea that given enough information, enough precise measurements, we can precisely know everything. Maybe our detectors may be off, but in principle we could. And this is telling us, nope, you can't even do it in principle. It's not actually possible. It's a whole different way of thinking about the universe. And this was something that was first pointed out by the famous German physicist, Heisenberg, not the one from Breaking Bad, but the real one. And so this really was that moment in science where everything changed about how we thought about the whole universe. And this was not something that's easy to accept. So if you think this is a really strange idea, you're right. It's kind of like saying, okay, let's say you talk about your GPS in your car, and you have a situation where if you precisely know exactly where your car is, you don't know which direction you're driving. Your GPS can't tell you, perhaps, or how fast you're going. And if you know exactly your speed and direction, you won't know where you're located. That would be a very strange GPS, right? You would agree? Yeah? It's like not quite what we can even imagine. What does that even mean, to not know everything about your position and your momentum? And the more you know your position, the less you know your momentum. Now, luckily, our car's GPS works because on our human scales, the uncertainty principle is too small. So the uncertainty doesn't really matter. But at electron and photon and atom scales, it really does matter. So it becomes really important, and this makes things very difficult because all of our assumptions about precision sort of go out of the window. And so if you're confused about it, you're in good company. Scientists were confused about it for a very, very long time. And so from that arose a very tried and tested technique called shut up and calculate, which is, we don't quite understand what it means, but we can actually do a lot with it. Luckily for us, we have equations. The mathematics is very clear. There's nothing imprecise about the mathematics of imprecision, which is really amazing. So given the mathematics, we can calculate many things. We can figure out the chemistry of the universe, structure of materials. We can build chips and electronics and lasers and all of the technology we have today. So we've already had a revolution, a quantum revolution, without really having to worry too much about this strange uncertainty that underlies everything. But, uncertainty is a strange thing, but actually in my life, as a physicist, this has been quite a common thing. Right? So, for example, when I started doing physics, my classes used to look like this a lot over the years. So I would often be the only woman in the room, and I'd have professors walk in and say, "Good morning, gentlemen." So this was, a rather worrying kind of experience, very much like how uncertainty was worrying. I was uncertain about whether I should be in that classroom, right? And I often considered the question of whether or not me as a woman could also be a physicist, right? Is there an uncertainty there, right? Maybe they're not compatible variables there. However, I'm here talking to you, so something convinced me to stay, and I want to tell you how I got to that point. So I thought, this question of whether or not I should be in the classroom should be approached scientifically. So let me ask a science question about who gets to be a physicist, who gets to be a scientist? And are there actual differences between all these, guys in the classroom and me as a woman? Is there a difference? Often we hear there are gender differences. But this is a scientific question, there must be data. So I went and started looking at all of the studies. And here's what I found. There's a lot of studies exploring the question of gender and other differences in how we do science. So let me show you a couple. They're quite interesting, as you'll see. Here's one study out of many, many. I can't show them all to you. Here's a study looking at infants. So we want to study all of the different age groups to see if there's ever really any difference as we grow and change over time. Are there any differences in the way we do science and our skill sets? So this is exploring counting abilities of 3-year-old children, boys versus girls. And as you can see, everybody's very good at counting till 3, and then everybody's equally bad after that, right? So that's really, for me, encouraging, because saying, well, when I was an infant, I could count well, or at least as good as the boys. So that made me happy. It wasn't on me. But then maybe over the years, as we grow older, things change. Again, this has been studied over and over and over again. Let me show you another such study, and this is for a different age group. This is for 8th grade students. This is from the US. I don't know if you can see much of it. The details are not that important. All it's showing is the scores on these national standardized tests. This is called the nation's report cards. And this is the test in mathematics, boys versus girls. And you see over the years, going back to about 1990 to 2019, there's been a slow kind of improvement in scores, but also a narrowing in any kind of gaps that there were. Right? So there's really no big difference. And if this was an inherent difference between boys and girls, it would always remain there. Right? And what you see here is that the difference doesn't remain. It has gone away. I think the biggest story here is that proficient is way up here. So that's a bit worrying that nobody's proficient. So yeah, maybe that's what we should really be focusing on, rather than whether girls or boys can do science. Anyway, again, for me, this is good news, because it says there really isn't a reason for me not to be in that 8th grade classroom. And you can look at many more such studies. I'll just show you one more. This is across countries, so that the previous graph showed you the US situation. If you look across countries at standardized tests, across many countries, you see that in some countries, these are scores where the bars below the horizontal are where girls perform better. And the bigger the bar, the bigger the difference. And then above means boys have performed better in this particular science test. And you see there's a pretty big spread. It's not that there's an inherent difference where in every country, either girls do better or boys do better. That would be an actual systematic difference. But that is not the case. It's clear that context is what's important. It depends on which country you are. And if you're interested, I believe Canada is somewhere here. So there's a slight bar above the horizontal. So boys perform slightly better, but in the most recent test, there's more recent studies now that show that that bar has disappeared. So things change over time. Context is important, and again, for me, this is very good news. So then why is there this difference when you go in the classroom and there's fewer girls and boys if all of the performance and skills are all the same? Well, there are differences in some other things, such as perceptions and environment. So, for example, there are many things that influence us when we are kids and choosing what we want to do, what we want to be as we grow older. Here's a really interesting study where these group of researchers put cameras in a science museum and observed how parents interact with their kids in the science museum. And what they found was that universally, both moms and dads spent 3 times longer explaining science to their sons than their daughters. Not because they planned to do that, it wasn't deliberate, They are perfectly well-intentioned parents, but this is what happens. This is what we call our unconscious biases. These are behavior patterns that we're not even aware of. And these influence what those young boys and those young girls will choose as they go forward with their careers. So that's definitely a difference. But again, to me, this is good news. Why? Because we can change our behavior, of course, and be much more aware of how we interact and what our biases are when we interact with science and with all of the people who are our mentors, as well as those we mentor ourselves. Here's another really interesting study. It's a very famous one called the Draw a Scientist test. And it's exactly what you think it is. Students are asked to draw a scientist doing science. What do you think they draw? Albert Einstein? Okay. Yeah? Generally? Yeah, okay, so they draw a variety of things, but there's definitely patterns. I'll show you one of my favorites here. It's more than Albert Einstein. It's usually a mad scientist, Albert Einstein. And usually there's something dangerous there, too. There's all kinds of stereotypes of science happening here. So the first such study was done in 1983 with about 5,000 students. Do you know how many drew women out of those students?
0.
Oh, you guys are very cynical. Very small numbers. So 28 girls out of 5,000 drew a woman scientist. 0 boys drew a scientist. That was in 1983. Things have changed, luckily, over time. And so I wanted to tell you about another study based on this Draw a Scientist test, where this teacher brought in, actually the teacher did the Draw a Scientist test, and then a few weeks later she brought in a woman scientist to the class to talk about her science, and deliberately this woman scientist was not wearing a white lab coat because that's a pretty stereotypical look for scientists, so she wore something else, and she didn't talk about the Draw a Scientist test at all, but did her science and interacted with the students, and then many weeks later the students were asked to do the Draw a Scientist test again, and this is what they started to draw. Yay, right? So this is, again, good news. We can change behaviors. This is not something that is written in stone. Humans are very easy to manipulate. So this makes me very happy. I'm telling you, this is all a good news story. So given all of this, there's also more sort of general studies. Since we're talking physics, let me tell you about a physics study which explored the environment for women physicists in the field. And across the board, across about 130 countries, these studies showed that there's certainly differences in access to resources, the burden of doing the majority of the housework, and also the progression in your career. So there are differences, and all of them can be addressed by us through actual changes in our system. So again, nothing there that is bad news. I think of this all as good news. And there's even better news. So there was one more question that was asked to all of the participants in these surveys. We're talking about thousands of participants. And they were asked, why do you do physics? If there's so many barriers, then why would you do physics? And across the board, men gave the same answer as, women gave the same answer as the men would. What do you think the answer was? Well, exactly. Women do physics because they love it. So that really, for me, was an inspiration. It means, yes, I love physics. I didn't see any inherent reasons for me not to do it. And I saw lots of things that could be improved to build a much, much more inclusive community. So I jumped in, and the other thing that I found very inspiring was to actually go and find out about women physicists who have made contributions. So here's one of my favorites. This is Cecilia Payne-Gaposchkin, who in the early 1900s, when quantum theory was a fairly young evolving theory, used the theory to show that all of the stars in the universe are basically made of mostly hydrogen and a little bit of helium. She used this theory to do that. That's quite a big thing, right? To find something universal about all of the stars in the universe. And she did this. Amazing woman, eventually became the first woman to be chair of any department at Harvard. So that's the level of contribution that women can make. So again, all full of inspiration for me. And then the final inspiration came from quantum physics itself. So let's go back to what we were talking about, which was uncertainty principle, which, as I told you, for years and years and years, scientists were quite uncomfortable with, and rightly so, because this is really hard. It's not something that is intuitive or something we experience in our everyday world. So it doesn't come naturally to us. So there was some level of, let's ignore it, except for some few scientists, until about the 80s when something changed. So this talk is called Quantum Revolution. So the revolution I want to talk about first is a revolutionary idea. And usually revolutions start as ideas, right? And the idea here was not to have a new theory, but to reframe what we thought about the current theory, which was quantum theory with all of its strangeness, and say, well, why don't we take all these things that we think of as bugs and instead think of them as features? So what if uncertainty has power, right? What if it's a resource, right? And so that's what people started exploring. And from that idea came something really amazing. It took until the 80s. Remember that quantum theory is much older. It's, first started being developed at the end of the 19th century, right? So it took all of that time for us to be able to change our approach and our thinking about this theory and realize, wait, there's power there. Precision and certainty, yes, that has worked well for us, but there's more to it. If you throw in a bit of uncertainty, maybe it's a good thing. For example, maybe uncertainty is a good thing when you don't want somebody to know something, which is exactly what you want to do in encryption, right? You don't want people to know your data. So what if you could use uncertainty in such a way, or quantum theory, to be able to encrypt data? And so that was proposed in the 80s, and that led to what's called a protocol called quantum key distribution, which turns out to be a way for, let's say, two parties, Alice and Bob, to be able to share a secret key that only they have and nobody else can steal it. And part of the way they do it is to use the quantum properties, encode this key within quantum properties in such a way that if somebody tried to hack it or listen in, then they couldn't actually perfectly copy the information. So part of the reason is because there's this fundamental fuzziness to quantum information, so that anybody who's trying to copy just cannot do it perfectly. Not only can they not do it perfectly, they will be detected for sure. So this is a completely different way to think about encryption, because we don't have to worry about some very powerful supercomputer coming to crack this system, because it has nothing to do with powerful computing. It has everything to do with not being able to get around the laws of quantum physics. You can't get around fuzziness. You can't get around this rule that quantum information cannot be copied. That's how you can keep your information safe. So that was quite a revolutionary idea. Now, actually, in this whole field of quantum information theory, which is where I work, it's sort of become fairly standard to think about it. But really, if you think about it, that's quite an amazing idea. When you can rethink something that's pretty, been around for a long time, but reframe it in a way that's powerful. And this is not just a theoretical idea. This is something that is being implemented in countries around the world. Companies are developing technology based on these ideas of quantum key distribution and also other forms of quantum cryptography, quantum communication. But this is I was talking about individual particles and the properties, the precise properties of those particles. Things are much more interesting when quantum particles start talking to each other. So for example, if you have two particles that have interacted with each other, what happens is this really amazing thing where they can sort of get locked together, kind of like gloves, pairs of gloves or pairs of socks, where they're completely paired up and locked. However, individually, they still have this quantum fuzziness, meaning they're not perfectly precise in all of their identity. So it's this beautiful balancing act of uncertainty, as well as certainly because the joint information about the pair of them together is perfectly clear and precise. Just like if you have a left glove, you definitely have a right glove. So in that sense, they are locked together, but individually, they don't really have their own precise identity. They keep their fluidity. And that balancing act is what we call entanglement. And that's even more powerful. If you think of that as very strange, yes, it is. But now we're reframing, remember? So in this new way of thinking, entanglement is not just strange. Entanglement, which originally, by the way, was described by Einstein as a way to prove quantum theory wrong because it was so strange. That entanglement now is considered a resource. And it really is. Turns out you can do amazing things with quantum entanglement. So I'll show you this photo, something that I loved as a child, the idea of teleporting to different worlds, Star Trek, the only show I was allowed to watch as a child in India, so it brings back wonderful memories for me. Teleportation, well, however, keep in mind that we cannot teleport like Star Trek. Human beings are not being teleported anywhere. But entanglement actually allows teleportation of information, quantum information, from one location to another, where the entangled channel is what transmits the quantum information, and the regular channel, if you like, such as Wi-Fi or your wired connections, are only used to tell the receiver how to set their teleportation device. Nothing about the actual information itself. So it's a whole new way of transmitting information that cannot be done with regular fax machines or Wi-Fi or anything like this. So that's really exciting. As I said, it's not faster than light or anything like this because you still need to send some signals, but it's not typically what we do with communication today, and it cannot be done without using some kind of quantum entanglement. Turns out it's more than just a fun thing you can do. It's a useful thing to incorporate into things like quantum computing and other kinds of communication protocols. So we can't do this, Star Trek teleportation. This is not real, but this kind of is already. So the photo is not real, though. It's supposed to be, it's a rendering, I guess, trying to show the Chinese quantum satellite that was launched, specifically to be able to generate entangled photons, particles of light, and transmit them to different locations on Earth and test that they remain entangled. And that was done successfully, and entanglement was demonstrated. And this would be the first step towards building some kind of a quantum entangled channel for doing communication in the future, which is kind of amazing that we are at that point. And what's even more amazing, and this is not something I think that most researchers in the field would have predicted that we would have by now, but we do. We have working quantum computers that can be accessed through the cloud by researchers and educators all over the world. So here, for example, is a photo of IBM's quantum computer. And this huge big thing here is where the computer is, and inside it looks really cool, I guess, and futuristic, but really that's not the computer itself. It's just the cooling system. Turns out that to make this computer work, you need to cool it to be colder than outer space. No big deal. So that's really hard and challenging. This is why we don't have very powerful, large-scale quantum computers yet. This is what we would call a prototype, kind of like a toy computer, kind of like back in the, when the first of our regular computers were first being developed, ENIAC and so on. Right? Those were like these giant machines and needed lots of care and maintenance. We're kind of at the ENIAC stage, I guess, with quantum computers today. But this computer does do interesting quantum kinds of calculations. Now, you may have heard in the news a while back, Google, who also has built a quantum processor, announced that they had proved something called quantum supremacy. which is this idea that they were able to solve a very complicated problem that you cannot do with current quantum computers. Turns out it is complicated to explain, at least. So instead of telling you about that, I thought I'd show you a much simpler quantum computing task that my research team did using IBM Q. And that also actually shows you can do things even with this simple, fairly basic quantum computer that you still can't do with regular computers and regular resources. So here's what we did. It's what we call decision making. So really, this is like a game where there are 3 players, and each of them is given up some information, and they're not allowed to talk to each other once the game has started. They can talk ahead of time to come up with strategies of how they're going to play the game. But once the game starts, they're not allowed to talk to each other. Right? So the 3 players have some information given to them, and then based on that information, they have to make a decision together, jointly, although they are not talking. And there are some conditions they have to satisfy. If they make the right decision, they win the game. If they don't, they lose the game. So I don't want to go into too many details of what the rules are, but the idea is if they plan ahead of time, what are their strategies based on what information they get, using regular communication channels and not being able to talk to each other once the game starts, they can win this game 75% of the time. But if the 3 players also have an entangled channel, meaning they pre-share entanglement, and after that they don't talk to each other, but they kind of do because they have entanglement, right? They have a connection, which is not a connection. So if they use the entangled channel, then based on the information they get, even without talking to each other after the game starts, they can actually make the right decision 100% of the time. So that's quite a difference. So what we did was we simulated this on IBM's quantum computer. There's not actually 3 different computers that we can use, but within IBM's computer, just like you simulate chess on a computer, we can simulate a quantum game. And we did this, and what you see here is actual data, where the orange line is the 100% success rate, which we didn't reach. The actual data from IBM's computer is the gray line. And then what we call the regular game without any entanglement, we call the classical game, that's the blue line. And you see the blue line is at around 75%. And what's interesting is that the gray line is not 100%, but it's certainly higher than 75%. There's a bit of a gap there, right? Why doesn't it hit 100%? Well, IBM's computer, unfortunately, has a lot of noise. And they have a hard time keeping that computer colder than outer space. Understandably so, but these things are improving all the time. But there's enough data there that the noise, the difference between the blue line and the gray line is outside of the error bars. So there's a clear quantum advantage you can see even in this kind of simple game, which you cannot see if you don't allow this entangled channel. So even these basic quantum computers are enough for us to be able to show and demonstrate that there are quantum tasks we can do using these algorithms. Well, I should say they're regular tasks that we can use quantum algorithms to do better. So that's really exciting. Given our current state of technology today with IBM's computer and Google's computer and what China is doing and many other countries, where do we go next, I guess, is the question we would all like to answer. So I think there's going to be stages of development of this kind of technology. In the near term, we're not going to suddenly have large-scale, powerful quantum computers, because the engineering needed would be really huge, and the resources, the cost, we don't really know if those things scale very well as yet. But there are many major research groups as well as industry R&D teams working on the problem. So as these computers start getting better and better, maybe we can solve some of the near-term, smaller-scale problems. For example, one of the things that turns out to be really hard to do on regular computers is to very precisely analyze molecules with a few number of atoms. So if you go to more than, let's say, I believe it's like 50 atoms, turns out it's a really difficult thing to do even with supercomputers. However, quantum computers would be better. The reason regular computers are are not great at doing this is because being able to capture all these quantum properties that I talked about and simulate everything about the quantum uncertainties, entanglement, takes a lot of computing power. But in a quantum computer, if you map the problem onto the quantum particles inside the computer, they have all those same properties. So you don't have to simulate them, they have them, right? So you just map the problem onto your quantum computer. This is what we call a quantum simulation. And the idea is that that would be a much more efficient way of trying to analyze these kinds of problems. So this would have lots of implications for, let's say, drug development, materials design, and things like this that are, of course, really, really high-impact kinds of applications. Another thing that we know that quantum does very well, we have an algorithm to do this, is actually search. So as you know, Google is all about searching, and mostly it's all about searching through very unsorted data. And Google's got it down. I mean, wow, right? You search for something, and in less than a second, you get all these results. But when you are talking about really big data, that's a real question, right, that we need to solve. As we create more and more data, the idea of how do we search and analyze data is a really important thing. And this is one of the reasons Google is very interested in developing quantum computers. So I very helpfully designed a quantum logo for Google once they build their quantum computers, because quantum search offers a speed up. And potentially, there are some problems that can definitely be much more improved if we can use quantum search algorithms. However, to actually do that kind of a quantum search on really large data requires a really large quantum computer. So this is a more long-term kind of goal, which will take much longer to be able to reach in the long term. So just to give you a more broad picture of what are the areas that people are focusing on to use all this power now that we are in this reframed mindset where we can think of all of these weird quantum features, quantum properties as features and that are powerful resources. What can we do with them? That turns out to be a really big question. Some of the areas that I've already talked about, one is, of course, communication, quantum security, quantum privacy, and so on. Teleportation falls in there, too. Talked about quantum computing a little bit. Large-scale quantum computers could also be able to do calculations like factoring, which would then hack all of our current passwords. So that's another area of ongoing research to see if that can be done. And if that's done, then keep in mind that even if it, let's say, takes a couple of decades to build a quantum computer that can actually factor large numbers. And I noticed, by the way, the algorithm that does the factoring of large numbers is Shor's algorithm, and it's on the board there. So I didn't write it, but that's good that it's there. So that may take a couple of decades, perhaps longer. But if that happens, and at that point, if all of our data is hackable, then we have to think about it now. Because, for example, there's a lot of our data which needs to have a shelf life longer than that, right? For example, our healthcare data, lots of other data that we have that we need over our lifetimes or longer, and they have to be safe. So if that data is being harvested and stored by whoever wants to hack it later, until a quantum computer is built, they can always go back and hack that data at that point, right? So that's a problem which needs an actual action to happen now. Not to mention, if we want to move away from the kind of encryption protocols we use today that are going to be vulnerable to quantum computers, it takes a long time to change infrastructure. In fact, it can take more than a decade to change over entire encryption standards. That's already happening, this discussion around what would be new encryption standards that are quantum safe. But that discussion has to start now, which is why there's a lot of activity in that area right now. Quantum sensing is another really interesting and very active field. Again, properties like entanglement allow for more high precision measurement, imaging, and so on. So these are areas that already there's a lot of technology being developed, and that's going to be a growing area, I think, in the near future even. By design, I'm talking about materials design and drug development and that area, quantum chemistry in general. It's also a huge area, which will be a big industry going forward, already is starting. And to me, perhaps the most exciting part of all this is thinking about quantum properties this way as being useful or powerful is actually a way to ask the question, what's quantum about quantum, right? Is there something quantum that's powerful, and why is it powerful? And that tells us something about the fundamental laws of the universe. And that's what really is exciting. Yes, it would be great to have powerful computers. Now, keep in mind that that doesn't mean all of you will have quantum laptops anytime soon. Because actually, honestly, to do email and WhatsApp and Instagram, you don't need quantum. So maybe in the back end for the encryption. So we're not going to be aiming for that. And if we have more powerful computers, yes, those would be great. But something much more exciting would be insight into those fundamental laws of the universe. So I think that's really sort of a broad overview of some of the areas that quantum science, quantum information will be impacting, in some of it more near term, some of it perhaps more long term. It's very hard to predict these things, and nobody should ever try to predict technology, because we always get it wrong. That being said, there's enough excitement right now that there's a lot of investment in building this technology. So here's, for example, a graph. I know there's a lot of information in here, but really what it's showing is that showing the amount of funding being put in by different governments around the world. So this is for research funding in quantum. That's what all those circles are. As you see, Canada is down here. I think this is a little bit outdated. There's a little more funding in Canada right now, committed to this. And so, as you can see, the EU has put in over $1 billion for developing quantum technology. The US investment cumulatively year to year over the next 5 years would be another $1 billion. What's also interesting is on the left-hand side, the axis shows the number of quantum-related publications per year, research publications. And look at that. It's now up at 10,000, which is kind of amazing. And also, the other thing I want to point out is that I found this nice plot in a Swiss quantum report. Switzerland has always been highly invested in quantum research. The Swiss actually used quantum encryption in one of their elections at some point to improve encryption, just to prove that this could be done. So they're very active in the area, but this summary actually is already outdated. So for example, the German funding shown here at 300 million euros is a little bit off because Germany recently announced another 700 million, which in US dollars, which will be in partnership with IBM and their quantum computing initiative. And that's not all. Just, I think it was a couple of weeks ago, India announced over $1 billion in funding into this area. But all of this just pales in comparison to what's already happening in China, which is over $10 billion of funding. So there's already a race happening, a quantum race, if you like. However, although there is that competition, researchers around the world do, of course, collaborate and work together on many of these problems at the academic level. There is also a quantum race on the industry side. So to give you an idea of what's happening, not just at the academic research funding level, but also developing the technologies on the commercial side, here's all of the different companies and startups that are already in the game. There are some major companies, as you see. I've already mentioned IBM, Google, Microsoft. These all have what we call full stack initiatives, where they're working to build the full quantum computer. But there are other companies that are working on building pieces of the hardware, pieces of the technology that would feed in to building a full quantum computer. That's a really big, interesting area of research because those technologies, of course, can be used for other things as well. And then there's the software side, the front end. Just like when you use regular computers, you don't go and actually open up your computer and turn on and off all of the transistors, right? You have some software that you use that does it for you. So similarly, we'll need to have front-end software for when this is available for people to program. So for example, the one that my team is familiar with with IBM is their software. They provide a means to program their quantum computer, and other companies have their own such front-end systems. The question is, we'll have to come up with something that's more standardized. We don't have it yet. It's early days, but there's a lot of work, as you can see, in the area. And the estimates currently is that this kind of quantum tech market on the industry side is going to be on the order of $18 billion in the next 5 years or so. As I said, these are all guesstimates, and trying to predict technology is always a very dangerous thing. But as you can see, that first revolution of idea is now leading to a revolution of technology. So who knows where we will go with all of the technology and how and what the impact will be. But the real revolution will be that third revolution, because all this technology will impact society, right? Look at what we're talking about. Talking about data, information, it rules the world as we know. Our healthcare, perhaps our environment, all of these big, big things that impact all aspects of society. So if we build technologies like these, they will transform society. That's the revolution. And that brings up more questions. Who will be part of this revolution? Who will develop the technology? Who will own it? Who will regulate it? And will we have a quantum society where everybody benefits equally from this? And how are we going to ensure that happens? Can we do something like that? Imagine if we could do that, if we are able to develop the technology and at the same time roll out an actual plan for how we can usefully have it improve society in every way. Wouldn't that be an amazing revolution? So in the end, that's the quantum revolution that I really want to see. Thank you very much.
We're now going to open the floor for questions. So please form a line to the mic here on your right. I'll ask you to limit yourself to one question and make sure it is concise and on topic. So while you guys are forming a line, we can start with our online audience, who has already sent in quite a few questions. So here's our first one. You mentioned a focus on near-term, smaller-scale problems in quantum computing. Do you have a prediction of when we might be looking beyond 50 to 100 qubits?
As I said, it's really dangerous, right? Technology, I mean, we always get it wrong. I mean, we're all supposed to have flying cars by now, right? We don't have that. However, based not on my own work per se, but on an overview of what all the different research groups as well as the industry groups and their claims, putting it all together, the numbers you were saying were, what, 50 to 100? Mm-hmm. I think we're talking in the next 5 to 10 years, probably 5.
Okay. I'll take another online question. This goes more to the graphs you were showing about the differences in gender. So that says, in one of the graphs you showed, you noted that we should maybe be less concerned about gender differences and more concerned with attaining proficiency. Do you have recommendations about how society should accomplish this?
Well, all these easy questions. Keep in mind that the data that I was showing was for the US education system. Canada, actually, when we do comparisons, and I can comment more on the Canadian system, of course, when we do comparisons and have these international tests, Canada typically scores actually within the top 5 of countries. So we're not doing that poorly, and I think we have reached proficiency on average. But broadly speaking, absolutely, I think we have to think about what builds a classroom where the maximum number of students can succeed. So, we have traditional methods, and they certainly work for certain groups in the class, but a lot of education research shows that, of course, not everybody is the same when it comes to learning. So I think we have to be much better about bringing in the latest research on education, how we learn, not to mention neuroscience, which has an impact on it, psychology, which, of course, has an impact on it. So a lot of learning is linked to human behavior. So we really need to bring that into the classroom in a better way to really understand how to maximize learning happening in all the classrooms. I personally am not an expert in the area, but there are experts, so let's talk to them.
Awesome. Question?
You had a chart there that showed different countries where girls did, or women did better than men in various tests. And I noticed that the ones where women did better looked like more than where men did better. Can you give us some of the biggies where the women really did well? Because I couldn't read any of the names on the bottom of the chart.
Yeah, so this is also a little bit outdated. I don't know what's the latest. So you want to know which countries the women really did well? Is that what the question is? We can go back.
Because they seem to be more of them than the ones that men did well in.
So again, I think that these numbers change quite a bit over time, and that's the point, because environments and contexts change quite a bit. So if you look at down there, we have Jordan, I think I'm sorry, even I can't read, sorry, this is a low resolution image. I don't think there's actually good research, and this is part of the problem, good research on what are the factors that lead to improvement or good scores by one gender over another.
I see Portugal, I see United States.
Now, if you want to know the numbers for the recent results, which was 2018, you can go on the website. It's the OECD website. And you can actually look at all kinds of breakdowns by country, even within each country, different regions and different types of breakdowns of which specific topic within math and science you're looking at. So there's a lot of information, and I really encourage you to go and look at it. There's a report analyzing it, and I think that will tell you more about the factors that go into this.
You see, if you wanted to invest your money somewhere well in terms of encouraging women to go into science, you probably need to find one of those countries which is relatively liberal and put the money into there, right?
Well, as I said, I think there are many factors to what determines this, and the thing we need to invest money is to actually get that data, and that's something we are doing here in Canada. We are now building up what we call the Dimensions program to be able to analyze what's happening, at least with respect to building more of a diverse scientific society. So hopefully we will collect that data and have a better picture. Part of the reason I can't answer it because we don't have the data.
Sure, take another question.
Hi, you were speaking earlier about preparing for the future of encryption with power being higher and higher. How susceptible do you think one-time pad would be to quantum computing?
How susceptible would one-time pad be?
One-time pad, yeah. One-time
pad is not susceptible. I mean, that's the point, right? So even when you have, let's say, when you create a quantum key, well, not a quantum, a key based on quantum key distribution, right? Use quantum techniques to create a secret key. You use this secret key in a one-time pad situation, and then you throw it away, and then you use another key.
So we don't have to start running for the hills. We'll still have some sort of
If you're using one-time pad and you know that the key that you used for one-time pad is already secure, then you're good.
And you're good.
The problem is that you can't always be secure, right? So the making sure that the key is secure is really critical, and there's no known completely unhackable method other than this, fully implemented quantum key distribution, which actually is not there yet.
Okay, thank you.
We'll take another question from our online audience. Are there any new discoveries on what may be at play when quantum entanglement is taking place? When there are such differences between entangled particles, what mechanism is at play for one to affect the other?
The mechanism of entanglement, I think, is the question. That's a great question. In fact, people have, different theories about the process of entanglement. However, it's not possible really to test them, right? So part of what's happening is that researchers are trying to develop ways to figure out what's the mechanism. For example, is it somehow that there is actually some connection that we don't know of through some other dimension, for example? That's perhaps a potential theory. How do we test any of this? That's really when we will be able to know what's the right mechanism at all. It's an ongoing research problem. I can't tell you much more because right now there isn't any really well understood mechanism.
There's actually a related question here. How do you entangle the particles anyway?
So it depends on what kind of particles you're trying to entangle. So the most common source of entangled particles are entanglement of photons. So pairs of photons, which are particles of light, that are entangled. And the way that you generate these kinds of entangled particles is that you use lasers and you shine them at these special crystals, and you make sure to control the parameters in such a way that every once in a while, one of the incoming laser photons, particles, is absorbed in the crystal and it's re-emitted. Remember, that's energy coming in. So because of conservation of energy, that energy has to be emitted again. And the emission is not as one particle, but a pair of particles. It turns out those pairs of particles actually are entangled in certain properties, for example, the polarization, and they have certain relationships between the two of them because they were born out of the same single photon. So that's one of the most common ways to generate entanglement.
Question?
Yeah, I was reading an article this week that I didn't understand. It was talking about black holes suck all information and destroy it. But they're talking about an experiment of creating like miniature black holes in the lab, and they suck information into this black hole, they entangle the black holes, and it comes out the other end. Have you heard of that at all?
I have not read that particular.
I read it in the Atlantic magazine this week.
Okay.
So I guess you can't explain it to me then.
I'm sorry. I'll go read the Atlantic.
Do I get bonus marks for stumping do I get bonus marks for stumping the speaker or not? No?
Well, I'll reserve the right to get back to you.
Perfect. Thanks.
We'll take another question from the online. Could quantum computing shed light on the measurement problem?
Wow, such easy questions. So that's, again, I can't predict exactly what quantum computing can or cannot do, but the computing piece is based on applying the current laws we know of quantum theory, nothing new, right? Now, the measurement problem really is a problem because we know that when we observe a quantum system, in a sense, we change it because we get more information about it because we're observing it. So our description of that system actually has to be updated, right? And that can be a very sudden change, right? Where we don't know anything about it, and then we know exactly what it is, right? And why does that sudden change? Does that mean that the system itself suddenly changes? Or is it just our information changing? There's those kinds of interpretation questions that we don't understand. The theory, however, is the same, regardless of how we choose to interpret it. The measurement is really an interpretational problem. And so computing itself, at least the algorithms that you're developing, are not really going to change how the theory mathematically works, right? So I don't see personally how that will overcome the measurement problem, because that's part of how we apply the theory anyway. So it's the best I can do. Yes.
You talked about the processing power of quantum computing being able to decrypt large prime numbers. How much of a realistic threat if somebody that fell into the wrong hands? I mean, every credit card transaction that takes place uses that mechanism. How realistic a threat is it for somebody to use quantum computing to hack financial transactions?
Okay, so the scale of the quantum computer you would need to be able to hack current encryption protocols, we're talking about having a computer that has on the order of thousands of quantum bits, which are called qubits. The current computers that exist, for example, Google and IBM and so on, we're talking about on the order of maximum 50 qubits. So that gives you an idea of how far we are from where we need to be. How long will it take to get there? That's a matter of how the technology develops, right? So if there's sudden breakthroughs which make scalability easy, for example, if we find materials that work at room temperature, right? So for building the kinds of superconducting qubit-based computers that IBM and others are building, then that would be the kind of huge breakthrough that perhaps would make scalability possible. So it's hard to predict whether it's going to be that sudden breakthrough or whether it'll just be a slow increase in improvement in engineering that gets us close. That's up to the engineers, I guess.
So we don't really know. But the system's not going to collapse all at once. But there's a minor possibility that it could. If somebody made a significant advancement and it was done by nefarious people.
Well, it doesn't have to be done by nefarious people. It could be done by perfectly well-intentioned people and then bought by nefarious people.
Sure. But I mean, if it fell into the wrong hands, I mean, if a rogue government or something that developed it, then theoretically, but it's not very likely is what I'm hearing.
Well, again, as I keep saying, it's hard to predict how likely or unlikely it is based on where the technology is now. If there's certain improvements, then that could happen. Also, there are other types of platforms being explored to build a quantum computer. It doesn't all have to be based on scaling up what's currently being done. So there are other possible ways of developing this quantum computer. And if those happen to be the right ways, then maybe we will be able to have scalable computers. Regardless of that, even if it doesn't seem likely in the next 5 years, which is certainly the case, and it's perhaps more likely in 10 years or 20 years or whatever is the scale, when it happens, and all of your passwords are vulnerable, you don't want to wait till then, and then the day after that, somehow change your passwords and hope for the best. We'll have to be able to already have an entire infrastructure built up where the standard systems we use have already moved to new systems that are already quantum safe. And that takes time. So the time required to build a quantum computer will be roughly the same as the time required to change over from what we have now. So this is part of why we should be thinking hard about it. What's the worst that could happen? We change our systems, and then somehow, for whatever reason, a quantum computer never is built. But we still have a pretty good, secure new system. So there's not really a downside to that.
Okay.
Okay, well, I think we'll wrap up tonight's lecture. Please join me in thanking Dr. Shohini Ghose again. We can do this.